And I think that's time now to move to the next presentation. Thank you, Jonathan. We have a hybrid team of presenters for the second presentation. Pouyan will be hosting the presentation from the room, and his two colleagues, Peter and Sahibbir, will join virtually. So, the floor is yours.
No. Oh, worked. Perfect. Great. Thank you very much. Pouyan Djahani from Aon Toronto, being joined by my esteemed colleagues Peter and Sahibbir. It's around 2 a.m. for them in Toronto. Thank you very much, guys, for joining. The topic is application of reinforcement learning to dynamic hedging of variable annuities. We're not going to get into variable annuities that much. It's more of the hedging side. So if there are any questions, please ask Jonathan about variable annuities. So this is work that the three of us have been doing for the last, I would say, 18 to 24 months. Just an overview of what we're presenting today. We want to introduce reinforcement learning to improve the effectiveness of dynamic hedging. We're going to show examples using exchange-traded put options of the S&P 500 and on simple variable annuity models as well, products, GMABs in particular. And we're going to compare the performance of reinforcement-based learning based techniques versus traditional methods, traditional approaches that are actually being used in the industry right now. We're going to show results that we obtained over 18 months on real market data, and basically show that potentially we can improve P&L and reduce transaction costs as well using reinforcement learning. So hedging of financial derivatives. So VAs, as you know, are complex products with embedded options. So Monte Carlo techniques need to be used for valuing and pricing variable annuities. There's no closed form solution, unfortunately. And dynamic hedging techniques are used for mitigating the risk and managing the capital markets risk for VAs. So there's been some groundbreaking work in the realm of hedging from the 70s, where Black-Scholes, Merton, all the great names in quant finance came up with these beautiful theories. And that's actually was the introduction. That's how whole derivatives industry actually took over, started. And however, since then, there's been a lot of improvements and enhancements also. So as you know, Black-Scholes and Merton came up with very simplistic ways of pricing options. They assumed like geometric Brownian motion for stock prices, no transactions costs, and then later on there was work by Leland that added transaction costs, and also other techniques, sticky delta, sticky strike techniques, stochastic volatility, Heston Bates with jump diffusion models. Those were used to try to kind of explain the volatility fat tails of stock returns, and there's been a lot of success there, obviously, and that's basically used widely in the industry. And now we're trying to extend that and see how we can use reinforcement learning techniques for that. So example of a variable annuity is a minimum GMAB, which is a minimum accumulation benefits. Basically, you get a lump sum at maturity, very similar to a put option. However, there are obviously additional complexities, like for modeling decrements, for roll-ups, ratchets, and other specifics of the variable annuity product that make it more complex than a simple put option. But in its limits, you can say it's very similar to a vanilla, European-style vanilla put option where it expires and basically the lump sum payment is actually made at expiry. What do we have here? Oh, okay. So this was just an introduction. I'd like my colleague Sahibbir, can you please take over? I think actually Peter. I think Peter's actually doing the next dozen slides. So.
Yes, thank you, Pouyan. And hello, everyone. Reinforcement learning, I just want to emphasize on the slide the classic setup work where you have an agent and there's an environment and it makes a choice and it's rewarded positively or negatively. And, that's what you can see at the bottom of this slide. It's a Markov decision-making process and it's a classic setup. And it's in discrete time as opposed to continuous time. On the next slide, Pouyan. All right, you can see here, really the agent, the idea is that it learns through balancing exploitation and, also exploration. So the agent will make choices and learn over time and try to, maximize the cumulative reward. And you can see gamma here, that's a weighting and discount factor between 0 and 1. So again, the agent explores and learns and keeps track of rewards and tries to maximize rewards through time in decision making. On the next slide, Pouyan, you can see the rewards are a function of the current state. So the state can be really anything, it's a Markov process. So, what's happening in that particular point in time. It could be the passage of time, the movement of the stock price, and the action, taken by the agent. It could be, well, I'm going to hold this much of a security or that much of a security. And then what happens is the next state evolves and the reward is given. And you can really, see here that the focus is on it's a dynamic programming problem, and it's trying to understand the best way to maximize cumulative rewards. On the next slide, Pouyan, you can see here that in the case of hedging, the question is really, given the current position of the liability or the thing you're trying to hedge, how much of the asset should you hold to optimally cover off your risk? And in our case, what we looked at was the profit and loss, the net P&L from the transaction in a nominal sense. So, how well did the agent do in maximizing nominal P&L over time? On the next slide, Pouyan, we can see there's kind of like a couple of horses in this race. The first horse is Black-Scholes. This is set up in the classical environment where there's lots of restrictions, like markets are frictionless, volatility is, constant. But, really for the AI agents, they have the ability to, look at different constructs and, make adjustments in the presence of things like transaction costs, which we'll get into in greater detail in the slides to come. On the next slide, Pouyan.
It's a delay. Okay.
Oh, sure. Thank you. We can kind of see the pseudocode for this, and this is the general setup for the problem. We're using, a Q function and a Q learning, and really, that's about a function approximation method. And essentially, this is, you can see, generate the epsilon greedy policy. This is this notion that I talked about exploration and exploitation, where sometimes a decision is random and you learn from that. And sometimes it's like, okay, well, I've learned a bit. I'm now going to exploit that, and the trade-off between the two. On the next slide, you can see here hedging put options. Really, in the setup of our experiments, we really look at a couple of things here. And one is the passage of time, that's T, and ST is the stock price at a particular point in time. And then NT is the holdings by the agent or by Black-Scholes. Those are the three things. And, what's important in this context is that the decision-making takes place where, if you look at the actions, they are discrete. There's about 101 choices that can be taken at any point in time, and we'll get into that a little further. And as well, the stock price, that's continuous. So we have continuous and discrete kind of states that we're examining. And here we can see the epsilon greedy policy that's used to generate This is where you take a random sample. If it's above or below a threshold, it will either exploit or explore. And this changes by batch. And I've talked a bit about this, that the state space is continuous because, you know, really the stock price can take any value because it's following geometric Brownian motion in its simplest setup. And the action space is discrete. And here, ST is modeled as geometric Brownian motion. And, you know, we can, you know, see that here. And the action space, really, there's integers between 100 and 0. So 100 would be, you know, you short the whole amount of the stock, and 0 would be you're not shorting anything at all. So there's 101 decision points. That's arbitrary, but that's what we used. On the next slide, you can see really just what I talked about. And if we look at slide 17, in this case, we're looking at an option that matures in 10 days and a rebalancing frequency of 5 times a day. And the strike of the put option is at the money. At the money means that the strike is equal to the current stock price. And here we can see some plots of really, you know, what our laboratory experiments showed, and that is that reinforcement learning in blue really does a better job of managing transaction costs, because you can compare it to the black shoals, the null, and you can see it really in the distribution of the P&L, where it is, you know, closer and centered around 0 as opposed to, you know, negative and about 200 in this case. So with this, I'll hand it back to, I believe, Pouyan. Yes.
Great, thank you, Peter. Okay, great. Thanks, Peter. So what we did was take the agents that Sahibbir and Peter were training, and we actually then took them from a laboratory environment and put them in a real world market environment. So what we did is we compared 3 trained agents, AI A through C. They're using methodology proposed by Hall, Professor Hall from the University of Toronto, and Coleman Ritter from NYU. And we actually used those agents. We didn't retrain them during the 18-month period. And we also used 2 standard delta hedging techniques that are widely used in the industry. These agents, the traditional ones, only differed in what we call the risk limits. So the first one actually would rebalance the underlying stock to hedge whenever there was a mismatch between the liability and the assets. And the other one actually allowed for 5% net difference between the two. So those are, in total, we had 5 different strategies. We actually started in August 19th in 2021 by selling 100 contracts at the 100 at the money contracts on the S&P 500 put options, and we basically sold them every month. So we closed a position one day before expiry, and then we actually opened a new options position and the new front month options. The hedge ratios were updated every 15 minutes. We're actually getting market data directly from Bloomberg. And if you do the math, we're around over 15,000 data points were actually analyzed over the 18-month period. So what happened here? We can't trade directly in the S&P 500, so we are using the S&P 500 SPDR ETFs, which are highly correlated with the daily returns of the S&P 500. We assume linear transaction costs. These are highly liquid instruments. So we kind of ignored second order effects like any n-square terms that you would see in the literature. We kind of didn't consider those. These are, as I said, they're highly liquid. So 90 million shares are traded on a daily basis. And as I mentioned, the 18-month period, it was great that we saw the options actually expired 9 times in the money and 9 times out of the money. So it was a nice distribution. It wasn't like 17 times in the money and 1 time out of the money. So it's basically spread across different moneyness levels. We saw a 25% drop from the high of around 4,800 to 3,600 during that period. And the realized volatility was around 21.7%, which is very close to the 21.9% over the past 5 years. And we saw periods of both very low volatility and very high volatility, and relatively high volatility. at around 6.6 and 31.6. One more time. Okay. Oops. This is very... Okay. So here we show the 5 different policies, 5 different strategies, and how the assets responded to the change in liability. So we have the scatter plots on the y-axis. I think on the x-axis you see the change in the underlying options positions, and on the y-axis you actually see how the assets were able to track the liability. In a perfect world, if we're perfectly hedged, you would see a trend line at 135 degrees. However, here there's obviously some differences. And the table over there, you can see what our R-square values were using the 2 traditional strategies and using the 3 reinforcement-based strategies. And as you can see, they're pretty close in terms of R-squared slope. However, the difference actually happens in the intercept. So maybe you can call it the alpha that was obtained here. But when we did like a hypothesis testing, we saw that we cannot reject, like all of them, we cannot reject the null hypothesis that they're all equal to 0. So that's kind of an interesting piece of information that came from this. But this shows how our assets were tracking our liability changes for the 5 different strategies. As Peter mentioned, the main metric was our net cumulative P&L. As you can see on the top over there, that is the net cumulative P&L for the 5 different strategies. AIB and AIC are outperforming the other ones. That's kind of interesting. This shows the assets and liabilities put together. This is our assets for the 5 different strategies, and this is liability. Obviously, liability is the same for all 5 different strategies. This shows how the option prices are moving, how our option portfolio is performing. And this shows the 18 different option months, what strikes, what the at-the-money strikes were, what the realized volatility was, if the options expired in the money or out of the money, and what is the net P&L over that month for each of the strategies, and what's the total net P&L for the different strategies. So we were able to come up with 2 agents, AIA, AIB, and AIC, that outperformed the other ones. AIC came up top 8 times, AIB 5 times during this 18-month period, and the other strategies didn't perform that well. And so what we've been looking at is up to, this basically shows the option month performance, and this shows now the daily P&L. So with AIB and AIC, we're able to achieve positive average net P&L, and the standard deviation, however, was very high. The probability of having positive daily returns was higher for these 2 strategies. However, the confidence interval of the daily net P&L included 0, and there were 373 observations, so that corresponds to the 18-month period to 373 days. So this is some interesting results that we're still processing.
Time is over. So maybe we can leave some of the observations for the Q&A session.
It's 16 minutes.
Technical team, the clock is not working actually because it doesn't show that. So I don't know, it shows like 15 minutes. So please check it. Yeah, so that was a basis for confusion. But we can start with QA session, and maybe if there are any observations you would like to add to so we still can handle it. And again, I encourage you to put your questions through the app. So, and if you did so, just give me so because I don't see anything yet here. So as we don't have questions in the app yet, so you can add your final observations, so we can, I think, handle it for 3-5 minutes, and then, yeah.
Oh, you can.
Yeah.
Okay, sure. So, how much time do we have left?
3-5 minutes.
So I would like Sahibbir, if he can please go go quickly to the VA part then.
Sure. So for hedging VAs, to extend the put option case, we construct the VA as a combination of put and call options, and we support complex persistency dynamics. To support complex persistency dynamics, the value of the put and call options is determined by a Monte Carlo simulation. So for Black-Scholes, hedging is conducted by computing the first order central finite difference of the value of each option with respect to the underlying stock price. For the AI agents, hedging is conducted by inference using a trained reinforcement learning agent corresponding to each option. Next slide, please. The training process for the agents is consistent with the put option case. However, in this case, we have multiple agents, one corresponding to each option. There's a total of 4 agents. This consists of 3 for the fees and 1 for the claim. The fees are modeled as EPS strike call options, where EPS is used in place of 0 to avoid divide by 0 errors. The claim is modeled as an at-the-money put option. Next slide, please. The variable annuity is then modeled as a linear combination of these options. The call options have a linear combination coefficient of minus p, indicating a fee representing 100p% of the underlying stock price. The put option has a linear combination coefficient of 1. Next slide, please. So the subsequent results are generated using the following parameters. So the claim is modeled as an at-the-money put option with maturity 12 months and a linear combination coefficient of 1. The fees are modeled as EPS strike call options with maturity 1, 2, and 3 months respectively with linear combination coefficient of minus 2% each. The rebalancing frequency is monthly. Next slide, please. So here we have the first case where decrements are 0, so the persistency factor is constant at 1. Next slide, please. On the left-hand side, we see the distribution of the P&L. So it appears that reinforcement learning is able to outperform Black-Scholes by achieving a higher mean P&L, but the trade-off is that the standard deviation is higher as well. So the higher mean and standard deviation are driven by the transaction costs, which we can observe on the right-hand side. So under reinforcement learning, the transaction costs are generally lower, but exhibit more variability. Next slide, please. Next, we have constant decrement. So now the persistency factor is downward sloping. Next slide, please. And here we see a similar result where the mean and standard deviation are higher. So we are able to outperform Black-Scholes using reinforcement learning, but at a trade-off of a higher standard deviation. But both the higher mean and standard deviation are driven by the transaction costs, which are generally lower under reinforcement learning, but exhibit more variability. Next slide, please. And lastly, we change the lapse to be dynamic. So now not only is the persistency factor downward sloping, it is also stochastic. Next slide, please. And here we see, so the dynamic lapse rates are determined by applying lapse shocks to the base lapse rate. Lapse shocks are computed using the moneyness, and the moneyness is based on the claim payment and is computed through time for each path. Next slide, please. Similar to before, we see reinforcement learning being able to outperform Black-Scholes by achieving a higher mean P&L, but at a trade-off of a higher standard deviation as well. And this is driven by the transaction costs observed on the right, which are generally lower for reinforcement learning, but exhibit more variability. Next slide, please. So next we wish to consider real-world market conditions. So we perform backtesting along one historical path using the trained reinforcement learning agents from the previous section. We use the same historical period as was used in the put option case. However, to reduce the computational requirement, we use 1 order of magnitude fewer time series data points, approximately 1,500 instead of 15,000. Hence, although the historical period is the same, the partition of the historical period is less granular. Next slide, please. The need to reduce the computational requirement arises from the need to perform Monte Carlo simulation to value the put and call options in the variable annuity case. To further reduce the computational requirement, the Monte Carlo simulation uses an additional 2 orders of magnitude fewer time steps, approximately 15 versus 1,500. Hence, the number of outer loop time steps is approximately 1,500, and the number of inner loop time steps is approximately 15. Next slide, please. To span the entire historical period and use time points consistent with the time series data, the timing of the claim and fee payments is modified as follows. Previously, the claim occurred at time 12 months, but now is increased to about 18.64 to span the entire historical period, and the fees are slightly adjusted from 1, 2, and 3 months respectively, such that they align with time points consistent with the time series data. Rebalancing takes place at each of the approximately 1,500 outer loop time steps. Next slide, please. The first case, we have once again 0 decrement, so the persistency is constant at 1. Next slide, please. On the left-hand side, we see the cumulative P&L across time, and we observe that reinforcement learning has a much higher terminal value compared to Black-Scholes, and this is driven by the transaction costs, which we can observe on the right-hand side, where reinforcement learning has much lower transaction costs relative to Black-Scholes. Next slide, please. Here we have constant decrement, so the persistency factor is downward sloping. Next slide, please. And similarly, we have a terminal cumulative P&L under reinforcement learning being much higher compared to Black-Scholes on the left-hand side. And the plot on the right-hand side shows how the transaction costs drive this P&L behavior, where reinforcement learning is able to achieve much lower transaction costs relative to Black-Scholes. Next slide, please. And finally, we consider dynamic lapse, where now the persistency factor is still downward sloping, but is no longer smooth due to the impact of the dynamic lapse. And in contrast to the previous section, we don't observe any stochasticity because we're only considering one historical path in the outer loop. Next slide, please. As in the previous section, dynamic lapse rates are determined by applying lapse shocks to the base lapse rate. The lapse shocks are computed using the moneyness, and the moneyness is based on the claim payment and is computed through time for each path. And next slide, please. And finally, we see similar results where the terminal cumulative P&L is much higher under reinforcement learning compared to Black-Scholes, driven by the transaction costs observed on the right, where reinforcement learning has much lower transaction costs compared to Black-Scholes. Now I'll hand it back to my colleague Pouyan.
Okay, so
Yeah.
these are the conclusions. Thank you.
So that was a real sprint. Thank you. We have time for one question. I don't see anything on the app, but I can't judge if that's because of the technology or... sorry. Still, okay. I ask you again from the practitioner's point of view, if this kind of approach is usable or feasible for the user in insurance company in a practical world, what are the challenges of any company?
Currently, I would say currently probably not. This is more like a black box kind of setting, so I don't think the regulators would be too happy to play with investors' money with this. But maybe with new regulation, things might change.